So call them capitals A, B, C, and they're fairly simple sets, right? They only have small numbers of elements, so we'll call that little a and this little b. Right? So set big A consists of just two elements, little a and little b, and set B consists of three elements, P, Q, and R. So that's P, that's Q, and that's R. And the third element, it consists of just two elements, S and T. Okay? And we're trying to find an example that answers this, is if F is injective and G is surjective, is GF surjective in general? Or is it injective in general for all cases, given this? So again, we're looking for a counterexample, right? So if we can show this is not surjective, then GF is not surjective in general. Right? And if we can find a counterexample, maybe the same one, save some work, if we can show that this is also not injective, the composite, GF, if it's not injective, then GF is not injective in general. So we cannot deduce that GF is surjective always or injective always. In the same way that we showed that if F and G are surjective, then H is always surjective. Right? So we find a counterexample, we can reject these. So we're building a counterexample right now. Okay, now, so obviously A maps to B. Well, I'll put in the actual mapping. So F, so this is function F, and here's your function G. Now F, now I'll put it explicitly the mappings. It maps A to P. Okay, so it maps A to P, and it maps B to Q. Right? Now, have a look at this mapping. This mapping F is of what type? Which of injective, surjective, bijective? Which is it? Well, it's obviously not surjective, right? Because this point here is not mapped to, so it's not surjective. How about injective? Yes, it is injective. Why? Because each element in your codomain, it's B, big B, is mapped to at most once. At most once. So, in other words, once or not at all. Once, not at all. Right? So F here is injective. Okay? So F is injective. So we have an example here of an injective function F. All right. Now G maps this set PQR into the set ST. Right? Let's see that from the diagram. And this is straight out of the text. And the actual mapping is G maps P to S. G maps P to S. Okay? And it also maps Q to S. Alright? And it maps R to T. Okay? Now you're given the actual detailed mappings here. Alright, now have a look at C. Can you see that each element here is mapped to? Right? So this G here is surjective. Okay, by definition. Surjective function maps, has every element in the codomain mapped to. Okay? So this set is covered in a sense. Every element is mapped to. Every element has at least one arrow going to that element. So this G is surjective. Okay? So F we said here was injective. So that's true. and G here covers every element, so G here is surjective. So that's true. So this this composite, so this H that's mapping A to C, is it surjective? Is it injective? Let's have a look. So we want H. Is it surjective? Have a look. Now we're mapping A. Now H is composite. Right? What type of function is it? So it's mapping A and B to S and T. Now is it this H here, this composite function? Is it surjective? So that means for each element, there's an element in A that maps to it, right? For all members of C. Well, look, S gets mapped to by A because A maps to P, P maps to S. So S is okay. So there's an element A that maps to S. But what about T? We can get this far, but then you're stuck. So all elements of A, big A, they all map to S. Right? There's no element here that maps to T. So from the point of view of this set, big A, there's no element that maps to T. Therefore, GF is not surjective. Okay? So this counterexample kills that. So we know that GF is, this composite function GF is not surjective. How about injective? Well, so if you're mapping from A to C, injective means at most one arrow to each member. But look, S here has two arrows. Right? Therefore, this mapping here is not injective because we've got two arrows coming to S, little s. So it's not injective either. Okay? So you can't conclude anything, right? And well, if it's not surjective or it's not injective, therefore it's not bijective. Okay. So you can't conclude anything, right? Now before I clean the board, we'll do theorem 29 and introduce to you the concept of the identity function. Well, what is 29? Well, first I guess I should start with the notion of the identity function, and you can probably guess just from its title what it is. It's a function that, in a sense, doesn't do anything. Right? It's sort of the lazy function, and you can probably guess its definition. So I'll write it down here. So the identity function, firstly, its symbol, it's just a capital I for identity, right? So, and usually have a little suffix here, capital A, because it's mapping from set A, your domain is A, and it maps from the set A to the set A. Right? So its domain and codomain are the same set. Right? So now this identity function has the following property. The rule part is the following: I of A of any element A is just the same. It doesn't change. Okay, so for all A belonging, little a belonging to big A. Right? So it takes an element, any element of A, let's say, and it just maps it. So yeah, here's an arbitrary element A, and it just maps it to the same element, right? So that's your function, your rule there. If it maps each element belonging to A, for all elements belonging to A, you get this. Then it's just like it maps to the same element, right? From little a to little a for all elements of your set. Okay, so that special function, because it's unusual, extremely unusual. Mostly things get mixed up. You know, if you're mapping from one set to the same set, usually your function will mix things up. Yeah, that's the most probable case. So this is an unusual function, and it's called the identity function. Now, theorem 29 says that if you have, I think I'll clean the board, so I'll stop there and continue on with this proof, and the proof is about the use of this identity function. And when I resume, I'll start talking about why am I talking about this stuff? Why am I talking about the identity function and so forth? And because you'll probably start getting a bit suspicious about the path I'm taking. There's good reason for going in this particular sequence, because there's a pot of gold at the end of the rainbow. So I'll stop here and clean the board.